All right, we're going to look at oxidation reduction reactions and talk about what's called a half reaction and how to balance these half reactions to see what's going on in both the oxidation reduction and to determine who's being oxidized, who's being reduced, who is the oxidizing agent, and who's the reducing agent. So the first step is to assign oxidation numbers, and if you need refresher, go back and look at the assigning oxidation number video. But when something's an element in its elemental state, its oxidation number is going to be assigned 0. So oxygen by itself is going to have a 0 oxidation number. In an ionic compound like magnesium oxide, then the ions have the charge they would normally have. Magnesium's in group 2, so we're going to assign it a 2+ oxidation. Oxygen, we're always going to assign a 2-. Right, and so just looking at it, we can see that the magnesium's oxidation state is going from 0 to +2. Oxygen is going from 0 to -2. So we have a change in oxidation number, so this looks like an oxidation reduction reaction. So what we're going to do is split the two different reactions in half, right? We're going to take our magnesium, here we have 2 magnesium, and they're becoming 2 magnesium cations in one of our reactions. The other reaction is we have this O2 and it's becoming 2 O2-, right? So at this point we have the number and type of atoms balanced, right? We have 2 magnesium on this side, 2 magnesium on this side of the arrow, 2 oxygen, 2 oxygen. So we've conserved matter. Now we need to talk about conserving the charge. And on this side of the equation, we have 2 magnesium. Each one has a +2, so we have a +4 charge. Here we have a 0 charge. So to make this side 0, we have 2 +2s. We need 4 -1s. So we're adding our 4 electrons to that side. Down here, this oxygen has 0. We have 2 oxygens with a -2, so we have a -4 charge on this side of the arrow. So we need to add 4 -1s on this side, so we add 4 electrons to that side of the equation. Now what we're going to try to remember is our Leo goes Gur, and the loss of electrons is oxidation. Right, so this magnesium here is losing electrons, so this is our oxidation. Here the oxygen is gaining electrons, so this is our reduction. Our reducing agent is the species that's oxidized, so magnesium is also your reducing agent, and oxygen is your oxidizing agent. Right, which is where oxidizing comes from, is from oxygen. So if we remember that the loss of electrons is oxidation, and we look at our periodic table, the things that are most likely to lose electrons are the least electronegative. So our metals are the ones that tend to be oxidized, and the gain of electrons is reduction, so our nonmetals tend to be reduced. So in an oxidation reduction reaction, the more electronegative thing, the nonmetals tend to gain those electrons because they're pulling them more tightly to themselves, and the metals tend to lose it. So kind of when you're looking at these equations as we move forward, you'll probably notice that the metals are typically the things being oxidized. All right, so here's another oxidation reduction reaction that we want to look at to try to figure out who's being oxidized, who's being reduced, and to balance that oxidation equation. So in this kind of oxidation reduction reaction, sometimes to write the half reactions, if we have an aqueous ionic species, it helps to write out the complete ionic equation. So then we write our zinc as a solid, and then realize that our copper becomes copper 2+ aqueous, plus SO4 2- aqueous, and it's going to Zn. Remember, zinc is always going to have a +2 charge. SO4 2- aqueous, and then our copper remains a solid. So one thing we may not have talked about yet is what's called a spectator ion, and that's an ion that doesn't take place in a reaction. It just is the same on both sides of the equation. It's a spectator. So if we kind of look here, on this side of our arrow we have this sulfate ion. On this side we have a sulfate ion, and so that's called the spectator ion, and it's really not doing anything but floating around in solution. So when we write our half reactions, we're just going to disregard it because there's no change in oxidation number in those species. But what we see is we have zinc here, and we would assign it a 0 oxidation number. Copper has a 2+, the zinc has a 2+, and now the copper has 0 because it's elemental copper. So one of our half reactions, we have zinc with a 0 charge becoming zinc with a 2+ charge. Our other one, we have copper with a 2+ charge, and now it's becoming elemental copper, so it has a 0 charge. All right, so we have two species that are changing oxidation number. We have the number and type of atoms balanced on both sides of our half reactions. Now we need to balance the charge. So on this side we have a 0 charge, here we have a +2, so we need to add two -1 charges, so we're going to add our electrons over there. Here we have a 0, here we have a +2, so we need to add two -1 charges here, and we're going to add two electrons there. And so what's really going on with this oxidation reduction is this zinc is taking two electrons and it's giving it to the copper, right? So the zinc is losing electrons, so this is being oxidized, and it's giving those two electrons to the copper 2+ cation, so it's being reduced. And again, so this is our reducing agent, and this is our oxidizing agent. All right, here's another oxidation reduction reaction we want to look at and try to balance. So we have solid zinc, we're adding it to hydrochloric acid, we're going to form zinc chloride and hydrogen gas. So if we look at our oxidation numbers, right, zinc is going to be 0, it's elemental. Hydrogen, we're going to give it a 1+, we said, and chlorine then has to have a 1-. Here our zinc always forms a 2+ cation, chlorine is going to be a 1-, and hydrogen is now elemental, so it has a 0 charge. So we can see that zinc is changing charge and hydrogen is changing charge. But we're going to write this out. We're going to split the aqueous components into their ions. So we're going to look at this as zinc solid plus 2H+ aqueous plus 2 chloride ions. It's going to form zinc cations plus 2 chloride plus some hydrogen gas over here, right? And so first thing we're going to do is look for our spectator ions. That's the thing that's the same on both sides. So these chloride ions are the same, so they're not changing oxidation number. They're not part of the oxidation reduction reaction. So in one half reaction we have zinc becoming zinc 2+. Here we have a 0 charge. Here it has a 2+. Then we have 2 protons, and they're becoming H2, so we have a 0 charge here. All right, so we have the number and type of atoms balanced on both halves of our half reaction. Here we have a +2 charge on this side of our arrow. Here we have a 0, so we have to add two -1 charges, 2 electrons here. Here we have 2 +1 charges and a 0 charge, so we have to add two -1 charges here. So zinc is losing electrons. This is our oxidation, this is our reduction, and those are your balanced half reactions. All right, here's an oxidation reduction reaction that should look familiar to those of you taking the lab. We take a copper wire, we suspend it in a silver nitrate solution, we come back in a week, we have copper ions in solution, and we have silver plated out onto the copper wire. All right, so first thing, let's write this out, splitting apart the aqueous species. So we'd have copper plus 2 silver plus 1. Silver is always going to be a +1. Plus we have a nitrate. We have 2 nitrates, NO3 minus. Becomes copper. Copper is going to have a 2+ because we have 2 -1s attached to it. Fingers are not erasers. NO3 minus plus solid silver. All right, so we have elemental component, elemental compound. So we're going to have 0 oxidation number there. Silver is +1 when it's ionic. Nitrate is -1 from our polyatomic ion table. Copper forms 2+ in this instance because you have 2 -1s here. And those are our oxidation numbers. We're going to find our spectator ion here. Nitrate isn't changing. It's the same on both sides, so we can take that out of consideration. What we haven't mentioned so far, right, is these tend to be single replacement reactions. So copper is just replacing the silver here. So this is a single displacement reaction. So one of our half reactions, we have copper, and we said it has a 0 oxidation number assigned to it. It's becoming copper 2+. Then we have silver that had a +1. It was a silver cation, and it's becoming a neutral silver atom, right? So we have the, no we don't. Put 2 there, 2 there. All right, so now we have the number and type of atoms balanced on both sides of our arrows in our half reactions. Now we have to balance the charge. So on this side of the arrow we have a 0 charge. Here we have a +2. So we're going to add 2 electrons to make this a 0 charge. Here we have 2 +1 charges, so +2 overall. Here we have 2 zeros, so 0. So we need to add a -2 to this side, so we're going to add 2 -1 charges, and we're going to add our 2 electrons, right? So remember, the loss of electrons is oxidation, so here's our oxidation. Gaining these 2 electrons is reduction. So we reduce from a +1 to a 0, so that's reduction. And this is our reducing agent and our oxidizing agent. Oh, lost track. All right, I think we have time for one more oxidation reduction before we reach our 15-minute time limit on YouTube. So let's look what happens when we take hydrogen gas, add it to chlorine gas, and form hydrochloric acid. So hydrogen is elemental, 0 oxidation number. Chlorine is elemental, 0 oxidation number. This is an aqueous species, so we'd have H2 plus Cl2 going to 2H plus 2Cl minus, right? So we're going from hydrogen having a 0 to a +1, chlorine having a 0 to a -1. So our 2 half reactions are H2 going to 2H plus and Cl2 going to 2Cl minus. And this one has something a little different that we haven't seen before. So we have the number and type of atoms balanced. We have 2 hydrogen, 2 hydrogen. We have 2 chlorine, 2 chlorine. Now we have to balance the charge. Right, so here we have a 0 oxidation number. Here we have 2 +1, so we have a +2 overall. So we need to add a -2, so we're going to add 2 electrons over here, and now we're balanced. Here we have a 0 charge, here we have a -2. So what's a little different here is we're not going to balance to 0. All of them so far we've balanced to 0, but all we've said is we have to have the charge balanced on both sides. That charge doesn't have to be 0 on both sides. So here we have a -2, so we need a -2 on this side, so we're going to add 2 -1s here. Right, so now this side has a -2 charge and this side has a -2 charge. So we're not always balancing both sides of the half reaction to 0, we're balancing it so the charge is balanced. All right, and so hydrogen is losing electrons, right, so this is your oxidation. Chlorine is gaining, so this is your reduction. So it's something a little different there. We weren't balancing to 0, we were balancing just the charge itself.